Hello. This is a video reply to Mr. Carlson's lab. Paul found out that the outside foil of a capacitor is not always what you might think it is. I'm going to show you the link to his YouTube video where he explains everything in great detail right here. Paul basically takes a capacitor, couples some hum into the capacitor by touching the outside with his finger, grounds one side of the capacitor and then measures with the oscilloscope how much hum is appearing on the other side. Then he turns the capacitor around, repeats the measurement, compares the two measurements, and the side that delivers the larger hum amplitude is obviously connected to the outside foil of the capacitor. This is a rather cumbersome procedure, and so Paul developed a circuit that automatically turns the capacitor around, and so you can very easily see on the oscilloscope which side is the outside foil. I thought you don't really need an oscilloscope, you don't need to see the actual waveform, you just need to know which side delivers the stronger signal. And so I developed a, what Paul later calls self-indicating foil side tester that just has an LED that shows you which side is the outside side. Paul then also developed such a tester. He calls it a SIFT, self-indicating foil side tester, and he published it on Patreon. It is copyrighted, and so I cannot tell you much about it here, but he uses an indicator that can show really the level of the hum, how strong it is, and so it's also again easy for you to decide which side is the outside. And now we come to this device. It looks pretty much the same. I can again ground the metal case. See, here, and I can turn it on the side. This one, okay. And you already see it's very sensitive. Like when I go with my finger here, this LED blinks. And when I go with my finger here, the other LED blinks. So we take the same capacitor again, put it in here, turn the device on. Which one? This was on. And we couple in some hum from the oscilloscope. And you see that this LED is lit. And if we look at it, then this is the side where I marked the outer foil side. Now we can try another capacitor. Maybe this one here, which I haven't tried before. So at first it has to equilibrate a little bit. Let's see. Oh no, very clearly. Very clearly this is the foil side as indicated. Let's, just for good measure, turn it around. Yeah, and you see, now since I turned it around, the other LED is on. I don't even need to touch the oscilloscope. Maybe I can even turn off the AC in here, which makes it much calmer. Touching again, yes. So clearly this side, which is the one that is marked on the capacitor, you can see it here, is indeed the outer foil side. Now this tester works completely different from Mr. Carlson's tester. The two LEDs don't blink back and forth to test one side or the other, but both sides are tested at the same time, and then the LED, which is connected on the side of the foil side, is the one that, the outer foil side, is the one that is lit. And I'm going to show you on the circuit diagram, because this is totally the invention of a friend of mine and myself, how this actually works. Okay, so here we are. I've set up a simple circuit here in LT-Spice. Here we have the hum source. That is basically just what's in the air, more or less. It's 50 Hertz and 5 volts, and we can use an oscilloscope probe here. And then we see it's a 5 volt amplitude, and it has 50 Hertz. Excellent. We'll couple this with a very small capacitor, which is basically the finger. So let's look on the other side. The amplitude has been greatly diminished because the impedance of this capacitor for 50 Hertz is rather high. And here we have our device under test. This is the 100 nanofarad capacitor. And we already looked here at one side. Let me just quickly delete those curves from the oscilloscope screen. So we'll look again here on this side. So never mind this little circuit here on the side. This is just basically ground here for our purposes right now. And those two very large resistors of 22 mega ohms, they just give the simulation a way to make everything with respect to ground. So let's look at the other side of our 100 nanofarad capacitor. Look at that. So here we have our amplitude, which is what? This is 2.82 volts up to, so something like 400 millivolts. Do I see this right? 100, 200, yeah, less than like 360 or something, 360 peak to peak. And the two curves basically are exactly on top of each other. Let me do this again so that you see this better. I delete the curves, and this time I start with the curve on the upper side here. Okay, so we have the very nice signal, and then I look on the bottom side of the capacitor, and it's the same. They totally overlap. So the idea of amplifying the two signals from the two sides of the capacitor may not have been such a great idea after all, because those two curves really are on top of each other. So now let's look at the capacitive resistance or reactance of that device under test. We all know the formula to compute that, and if we put in the 100 nanofarads and the 50 Hertz, which is the predominant hum frequency that we pick up with our body, we receive a value of 31 or 32 kilo ohms. By comparison, if we do the same, using the same formula, but this time for the hand capacitance of roughly 10 picofarads or maybe even less, we get to a value of 320 mega ohms. Now let's look at a simple equivalent circuit diagram of what we have there. We have our hum voltage of 5 volts. We have the hand capacitance, which translates to a resistance of 320 mega ohms. Then we have our device under test here, and we said it's 31 or 32 kilo ohms at that frequency, the capacitor of 100 nanofarads. And then we have two resistors, which basically go, as far as hum is concerned, to ground. And these two resistors are Rx. We want to know what is the best value for these resistors. We can use a program like Mathematica, fire it up, put in all the equations, and then we get this graph, and we see here Rx on the x-axis, and we see the differential voltage U1 minus U2 in microvolts, on the y-axis. And so we see the bigger we make the Rx resistors, the better it is. But if we are, say, at 50 kilo ohms, we are already pretty much at the highest, almost. And so that seems like a good value. 100 kilo ohms would also be a good value. It's not really critical. And these two resistors, Rx, also have another function, to which we will come in just a second. We know that we can look at the two voltages here. So this is node 4 and this is node 2. So we can also look at the differential voltage. We can say node 4 minus node 2. Show us that. And we have a voltage of about 200 and pretty much exactly 250 microvolts. Now if we change the values of these resistors, say let's go to 47K, good value, 47K. We have to run the simulation again. And we saw the amplitude went down a little bit, but very minuscule. We still have between 200 and 250 microvolts differential voltage. Let's just, for the fun of it, go down to 1K and see what we get there. Run the simulation again. Yeah. With 1K, we're down to 15 microvolts. That is really makes a difference. 200 microvolts or 15 microvolts, that's a difference. So that we shouldn't do. But 50K is fine. So now I'm back to LT Spice, and I have added some amplification to that circuit from before. We see the same resistors, the device under test, and the same hum source and hand capacity over here. But now I've added two operational amplifiers. Their plus inputs are basically grounded through 10K resistors. So they are in a circuit where they operate as an inverting amplifier. This is the inverting input. It goes here to the output. And to limit the amplification, but to a very high value, we have this 22 mega ohm resistor here in the feedback path. So now let's look what's happening here. Run the simulation. And we can look again at this input here. Very, very little here. We look at that one. That seems to be a little bit higher. But if you look at the oscilloscope screen here, you see they are very small. So what happened here? What's going on here? Let's look at the difference signal. This is node 2 and this is node 6. So we add the difference signal, node 2 minus node 6. That's of course centered around 0, so we don't see anything. We have to delete the other two. And I'll just run the simulation again. Oh, what's that? We only have 2 microvolts. Remember, we had 250 microvolts differential signal before, but now the difference is so much smaller. What happened here? Well, if we look at our circuit, we see that there is this feedback resistor, and that goes directly from the output to our device under test. Now what the operational amplifier wants to do, it actually wants to make the difference between the plus and minus inputs as small as possible by adjusting its output voltage, so that through the feedback, basically on the minus we have the same voltage as on the plus. Now what do we have on the plus? On the plus we have a constant voltage, which is actually here half of the operating voltage, the power source, which is 6 volts. So we have 3 volts here. We can look at this with the oscilloscope. Remove for a second again this difference. And so center this. Yes, we have 3 volts. Let's look at the positive input. It's absolutely on there. There is nothing on that line. It's 3 volts straight. So that's what the operational amplifier has to do. Actually, both of these operational amplifiers try to do the same thing. And when our signal arrives here at the negative inverting input, it gets amplified. Now let's look at the output here. At the output we have quite an amplitude. This is 3.36 volts plus and 2.66 volts in the valley here. So from 3 volts up to that's 360 millivolts that we have here. And what's happening? That is actually, you can't see the input signal anymore, it's too small. In phase inverted, that's why it was an inverting amplifier, and it cancels out whatever was here, so that this voltage here becomes so much smaller. Let's remove this again for a second. And see this voltage here, which is node 6, which we are not plotting here. Let's plot node 6. Look at this. This voltage here is now really small because of the feedback. And it gets even smaller when it has to go through the 31 kilo ohms of our device under test. And we divide it in half basically by this 47K resistor. And then it comes here to the inverting input of this one. Now let's look at it. You can't even see it anymore on the screen here. It's just a flat line. So we have, let's see what we have at the output of those 2 operational amplifiers. Let's look at the output of this one. Aha! So we do get some oscillation here, but if you look at the amplitude, it's very, very small. 110, it's like 1 millivolt. Still much bigger than what we had before, but very small. Now let's look at the output of the other amplifier. Oh, wow! Look at that. This is, we have seen it already, 360 millivolts compared to the 1 millivolt of the green line that we had before. Now this is a difference that we can work with. And why is that so? Well, if we look at the currents that are actually flowing through these incredibly large 22 mega ohm resistors, look at this. Here we have the current in the range of 50-60 picoamps flowing, and if we look at the other amplifier, we get a much larger current, which is also very small, in the range of 15 nanoamps, so 1000 times larger. And that is the reason why we actually have such vastly different voltages here. Now we are ready to look at the full circuit diagram. We recognize the some parts that we know already. This is the hum source, this is the hand capacitance, this here is the device under test, our 100 nanofarad capacitor. We have the 50 or 47 kilo ohm resistors here. A little hard to read, I don't know why that is the case here. And we have our operational amplifiers, inverting amplifiers, just as before, with the 22 mega ohm feedback resistors, a little hard to read. They have also gotten very small capacitors to suppress some wild oscillations at 300 Hertz. And I would say let's look at some signals. So we have again the 5 volt 50 Hertz signal here. Let's start by looking at the output of the amplifiers. So this is the first output. This one is now, you see like some startup effects here, and then it's like going to its steady state value, but it's a very low amplitude. Starts at 3 volts, very low amplitude. Let's look at the other one. Oscilloscope probe here. Yeah. Here we have the 200 millivolt or 230, 40 millivolts, while the other amplitude is really nothing. So now we have one output with a high amplitude here and one with a low amplitude here. So we use these coupling capacitors to actually help us correct the offset of the operational amplifiers. The reason is that they are not ideal, they are real parts, and they have not exactly the same amplification. That's not so bad, but they also tend to drift a little, and since they are running with very high amplification values, a very small voltage difference here, or let's say even if there is 0 voltage difference here, the amplifiers may already output some offset voltage, and that would screw us in the end, because it would like shift our circuit to one side or the other. So we use a capacitor here, again 100 nanofarads. That's a good value for 50 ohms, for 50 hertz, to get rid of that DC part. So we only have the AC part, which we see here. So one big AC part and one very, very small AC part. Now we have to detect how big they are, and we use a peak detector. The peak detector works with this diode here, and it doesn't matter that it has a minimum voltage of like 0.5, 0.6 or 0.7 volts in flow direction, because this operational amplifier in this circuit totally eliminates that. Watch out, we are coupling the signal to the positive non-inverting input. The inverting input gets back after the diode, and this feedback here totally eliminates the forward voltage of the diode. And then we have a capacitor here, which we charge up to the peak voltage. So let's look at the peak voltages. We delete these signals here. Let's see here. You typically see the capacitor charging up slowly. Remember, that was a very, very small amplitude. Let's look at this capacitor here. Aha, much better. This one is about 200 millivolts higher than the other one, and it gets charged in the 50 hertz with a 50 hertz frequency. So there's a little bit of ripple on there, but it doesn't really matter for us. Now we want to see which one is bigger, so we have to take the difference of the two. And this we do with this amplifier here, another operational amplifier, which is this time in a circuit where it doesn't have such a high amplification. Look here, 3.3 mega ohms, 1 mega ohm, so something like threefold. And it gets the two signals onto its two inputs. And now let's look at the difference output signal. Here we have it in red. So this is the output signal. It's now at 3.6 volts, something like this. And we'll come to this rest of the circuit later. Now I'll turn the, just remember it was at 3.6 volts. I turn the capacitor under test around. So I just remove, let's say, this wire here, and I make a new wire from here to here. Now I'm coupling onto the other side. And we run the simulation again. And we'll look what the output is this time. Aha! Now look at that. It's still running, but we see already that the red, which is the difference voltage, is now way below 3 volts. So 3 volts is kind of the, I don't really know which way we go. And one time the difference voltage is below 3 volts, 2.3 volts here. The other time it was above 3 volts, 3.6 volts. So that's what we see here at this difference point. Well, now we have to use a window comparator. We just compare it with some constant voltage, and that's what we do with these two operational amplifiers. Here we have the 6 volts power. We divide this down, 100k, then 10k to give a little bit of spacing between the two, so that if there is no device connected or there is no hum present, then no LED will be lit, because we will be in this in-between area, and then another 100k down to ground. We just couple in here with 1 mega ohm, and we take the two, this one has the non-inverting input and the other one has the inverting input connected to the difference signal. And so at one point, for one operational amplifier, the difference signal will be above the 3 volt line, or a little bit above 3 volt line, and for the other one it will be below. And the outputs are running in full amplification. There is no feedback, and the outputs are driving directly an LED, which is a high efficiency LED, and so we can use a relatively large resistor of 4.7K here, and then we see which LED is lit. Well, we can even look at this in the simulation. So let's remove what we have on the oscilloscope screen. This time we look at the current. Let's first look at the current of this LED. Femtoampere current. That's very small. This LED will not be lit. Let's look at the current of the other LED. Oh wow, look at that. Here we have 1.1 milliampere. And 1.1 milliamps for this LED means that it shines with a bright green light. This LED here indicates that this here is the outside foil end of this capacitor. Now let's switch it over. Remember, the top LED was the one that was brightly lit. We will remove this line again, and we'll add the capacitor to the other side. We'll run the simulation again. Before, the blue line was up. Now let's see what the output is this time. Look at that. And now the green line is up. The other LED gets the 1.1 milliampere and is brightly lit. Now what happens if we don't connect any hum to it, if our finger is not there? So we just cut this off. We do another simulation of that. And you see we have femtoamperes again. So both LEDs are actually turned off. This is the normal state of this detector. And now you also see why we needed these 50K resistors here. You have to see, this is the device under test, so these leads here are actually exposed. You touch them with your fingers. You may have some residual charge that you bring in here, and they are also directly connected to the inverting input of the operational amplifier. And if you wouldn't have these resistors, then this very charge, it could mean quite a bit of voltage here, which might eventually destroy your operational amplifiers here. You don't want that. But by having a rather low resistor to ground, here like 47K, all the charges that you bring here immediately flow to ground and can no longer damage the operational amplifiers. That's why we were using these resistors here. Now I already showed you the first prototype that I built here. This one. And can you see that? Yep. And it's sensitive to where you touch it. And if you look inside, where you see the batteries here, and you don't see the actual circuit. The actual circuit is like way up here, where the LEDs are, and it's in 3D wiring, free wiring technique. And I thought, well, this works so good, let's make a PCB board. So I used Eagle, and I sent the double-sided layout to JLC PCB. I'm not getting sponsored by them, but it was the first try that I did with them, and I have to say I am really happy. Probably can't really see it, maybe. And one side and the other. Well, it's the first one. A friend helped me make it. We made a couple of, not really mistakes, but like this close encounter here is totally unnecessary. We also forgot holes for actually mounting the PCB board. You don't think of that when you make it. It's for SMD. And I built one to try it out. It was actually a test for JLC PCB. And I put it into this enclosure, which is a free enclosure from a local company for hardware and stuff. And let's look inside. So this is what it looks inside. So we have the batteries here. The two shells are both grounded. Here we have the little PCB, and on the PCB, oh yeah, that's hard to see now, are the LEDs which directly connect through. Here you can see it. The electric connect through. And I'm gonna put in a picture of the PCB when it's in its fully populated state. Now let's give it a try and see if this works or not. So we have a switch here. Okay. And now I'm holding the case. I don't know if this will work. Yeah. And the other one, yes. Because now I'm grounding myself by holding the case. Let's grab one of those capacitors again. I don't know which one. Let's say this one here. I have to change the camera so that you can see that. Okay, now let's do it like this. Here's the capacitor. I already measured this one before. You can see on this side is the factory band, and yeah, let's see where we actually get the this LED has been already lit, and this is actually really the outside foil side. Let's turn it around. So okay, put it in the other way. Now if I touch it, alright, now the other LED is lit. That this one lights up without anything, I don't know why. Somehow this side gets more hum even if it's not the outside, but once I couple the hum directly to the foil, then the correct side, correct LED lights up. Okay, now JLC PCB was so kind to manufacture 10 PCB boards. I needed one for myself and one for my friend, so that should leave about 8 over, so maybe I keep another one, so 7, so I can at least give 5 to other people if you want them. JLC PCB, if you go through another YouTuber, Great Scott, you may know him, then you get the PCBs, 10 PCBs like this for something like €3 plus shipping. So I think it ends up for 8 or 9 euros for the 10 PCBs. Or if you are a first time customer, then you get this deal as well. And so I had to pay shipping on them, and so I'm willing to sell a few of those for a rather good price, maybe 3-4 euros each. I think it's only an interesting offer for those in Europe, because otherwise shipping gets too prohibitive, and then you're better off directly getting your own PCBs from JLC PCB. I will put the Eagle files and everything online. I will have the links underneath in the description, and so you can do this yourself, or if you just want one and save a few bucks, then you can contact me beforehand. Don't send any money, because I may already have sold them all. Okay, so that's the latest SIF tester, self-indicating foil side tester, and that shall be it. No more sifting, only testing capacitors. I'm happy with it. It's good enough. Thank you and goodbye. And if you are happy with this video, leave a comment. I would be happy to get a comment. Thank you.